Thanks very much. I'm Shep Dolman. For the past while, I've been directing the Event Horizon Telescope project, and it's a pleasure to be here with my two co-conspirators for this KISS workshop.
I'm Joe Lazio. Shortway is Chief Scientist of NASA's Deep Space Network. Longtime interest in VLBI, including space-based, and like Shep, very interested to see how this week progresses.
Hi, I'm Katie Bellman. I just recently started here as an assistant professor in the Computing and Mathematical Sciences department. And we're so happy that you came from near and far. So I guess with that, we'll get started. And thanks. So our first speaker today is going to be Kelly Holley-Bockelmann, and she's a professor at Vanderbilt University studying gravitational waves from merging supermassive black hole binaries, and she's also the team leader of the NASA LISA study team. So she's going to be telling us all about Black Hole 101, what we need to know about the basics of black holes. So with that, thank you.
Thank you so much. Good morning, y'all. I get to say y'all because I'm from Tennessee now. All right, so I was given the charge to basically set the stage and make sure we have a common vocabulary and outline a little bit about some of the big unsolved questions that have to do with black holes. And as I was adding things to my talk this morning, I thought, oh my Lord, there's no way I can cover everything. So let me just quickly do a check. Who in this audience are supermassive black hole experts or stellar mass black hole experts or black hole experts in general? A couple people don't like to raise their hands, but okay. So if I don't get to it, you can ask me, of course. And if I don't answer it, there are plenty of people who you can tag all week, apparently, to answer these types of questions. Okay, so first up, let me do some common misconceptions here. Because if you ask a physicist what is a black hole, they will give you a very different answer than what a typical astronomer will say when they talk about black holes. So I want to just make that very clear. And I'm not going to go over general relativity a whole bunch here other than in words, just to say that, that one of the great tenets of general relativity is that mass bends space-time. So very dense matter bends space-time very sharply. Very diffuse matter makes a bend in space-time rather shallowly. More mass bends space-time more, etc. And so if you ask a physicist what a black hole is a place in space-time where matter is so dense that the curvature of space-time is infinite. And if you're telling your little first grader friends about what a black hole is, and you tell them a black hole is a place where the velocity of escape is the speed of light. That's true, but it's a consequence of this. Because light has to travel on space-time. It has to travel on this little imaginary grid here. And so technically it just takes light an infinite amount of time to get to the place where the curvature of space-time is infinite, up here into flat space where you can measure it. So that's kind of a consequence of, oh my goodness, we're all going to fall asleep. Sorry. I will sing or talk loudly or something. Okay, so yes, there's a whole bunch of great relativistic consequences of this beautiful and simple description of a black hole. And it's quite mind-boggling, and I love it. One of the consequences is that, yes, matter bends space-time, but if matter moves and it's not perfectly spherically symmetric, then it makes a ripple in space-time. That is a gravitational wave. I am making a gravitational wave now. You can make a gravitational wave too if you feel like it. Okay, fine, don't. But here's a little description of what a ripple in space-time would look like. It literally squeezes and stretches space-time. Time literally slows down and speeds up and space gets smaller and larger. So the big deal is that if you have black holes, they make enormous ripples in space-time when you have two black holes merging. That is a great example of a non-spherically symmetric shape of space-time. It makes a great mass quadrupole that is time dependent, and that is what makes a great gravitational waves. And so there is a visualization of a numerical simulation of two equal mass supermassive black holes merging, and those little ripples that you saw were gravitational waves. And just note that if you noticed at the very beginning, there was a quadrupolar shape to these ripples, and that's kind of unlike the electromagnetic fields, which will make a dipole, right? So just trivia for those of you who like it. If you want to know more, you can ask lots of us. All right, so that is fascinating, and we are in the beautiful era, we are so very lucky, where we can actually detect some of that physicist description of a black hole. But if you ask a typical astronomer, at least historically, and still that idea pervades, if you ask a black hole, if you ask an astronomer, what is a black hole, they will typically point to objects like this. This is Cygnus X1, which is a stellar mass black hole. In a binary, it has 8 solar masses in its infinite curvature of space-timeness. But the big deal is that it's not dark at all. It's shining very brightly in X-rays. And so to an astronomer, we very rarely think about relativity. We think about parts of the surroundings of this black hole that shine, that emit data that we can observe and understand about it. So an astronomer view of a black hole, and this is data, this is an illustration. It's typically an accretion disk, sometimes jets, and the big deal is that we catch photons from the gas that is falling into the supermassive black hole that sort of heats up and shines in high energy photons. Sometimes you make a jet and you get different low energy photons and high energy photons that are excited by magnetic fields. Here is another view of that. Moving into higher mass black holes, this is a view of what a supermassive black hole looks like to an astronomer. So Meg Urry and company were part of this big way to classify supermassive black holes. This is not to scale. We just needed, the great artists needed to draw eyes on this black hole. So this will be probably smaller than this dot in physical scale. And all the stuff that we see are just the junk that falls in. You'll hear a lot about things like the accretion disk. This is that material that's kind of swirling in around the black hole, and the very most inner part of that accretion disk is where you can start to see some relativity talking to you in terms of fancy iron K alpha lines and that sort of thing. If you are interested in that topic, you can ask us. You typically see also a little torus that can obscure light. You'll see a jet. You'll see some clouds and clumps of gas that may be moving slowly. That's called the narrow line region, that it'll show up as narrow lines in the spectrum. And honestly, when I first learned this, I had a misnomer. I thought narrow line stuff was close to the black hole because narrow, I don't know, I thought narrow meant close together. Not true. The narrow line region in a spectra come from very slow moving gas far from the black hole. And you sometimes see some material that's moving very quickly close to the black hole, and that'll make very broad spectral lines because the gas is moving very quickly. This is not a perfect notation. Now we know that this picture has evolved. Among other things, we maybe think that these broad lines may not be actual clumps of matter rotating around. It may just be winds coming off of the outer part of the accretion disk. Anyway, this is still an evolving picture. But the big deal is that we think that this may be the anatomy around a supermassive black hole, and that astronomers' perspective gives you different types of observations and different types of what are called AGN, or active galactic nuclei. So for an astronomer, an AGN and a supermassive black hole are practically synonymous, okay? So for example, sometimes you get to see close in to the accretion disk and you get lots of high energy photons, and sometimes you stare straight down the jet, and that's called a blazar. So anyway, that kind of messy picture is what a typical astronomer will think of when you talk to them about supermassive black holes, around large black holes, or AGN, active galactic nuclei. So a word about size scales here. I kept saying things like far away and close in, and it's important for us to understand exactly what we mean by that, and so I'm going to give you some sort of fuzzy size scales. On this scale, sort of the black holeness part of the black hole, the Schwarzschild radius, et cetera, the place where relativity incredibly starts to matter, for a 10 to the 6 solar mass black holes, on the order of a couple solar systems-ish, right? Here, that is, the accretion disk is roughly 1 million times larger than that. And some of these jets can go out as large as the whole galaxy, which is, maybe even 10,000 times larger than that. So this part that we're calling the supermassive black hole is really a galaxy scale kind of consequence. Okie dokie. So we know that there are, for sure, 2 types of black holes. Okay? There are these stellar mass black holes that are a natural consequence of stellar evolution from very massive stars. And here is my very favorite movie that I love to show to first graders, et cetera. Only because that planet gets obliterated, and kids are very morbid, so they love watching that. Okay, so when you have a star that's 20 solar masses, 20 times larger than the sun or more, right? At the end of its life, when the core stops undergoing thermonuclear fusion, it can't support itself through radiation pressure anymore. It starts to collapse, becomes neutron degeneracy pressure, and a whole bunch of stuff happens. Eventually, the system goes supernova, blows its guts out into space, and the core that is left, if you don't lose very much of the core mass, ends up being a stellar mass black hole. Now, we know that this happens. And we know for sure that there are roughly 10 to the 8 of these floating around in our galaxy. Okay? So for those of you who are scared of black holes or want people to be scared of black holes, you can tell them that there's like 100 million of those black holes hanging around in our own galaxy. But space is big, so we're okay. Okay, so I just want to say a word about this because most of our understanding of those stellar mass black holes have gone under a huge revolution recently with gravitational waves. So now we're starting to see the marriage between the astronomer view of a black hole and a physicist view of the black holes, because we're starting to get real data that maps to the relativistic part of these black holes. Oh, apparently I'm not having any sound, so we can do that. You guys know by now it goes bloop. All right, so these were the consequence of, oh man, I'm going to get exact numbers wrong. I think it's 29 and 36, and I'm probably wrong. So 2 30-ish solar mass black holes merging together, and what we're catching are the gravitational waves from the very last in-spiral. In this case, you're well inside anywhere where you would get gas. So you're decoupled entirely from all of that astrophysical surrounding, in this case, and you're just seeing pure space-time. And it's beautiful data. This type of data encodes entirely different things than what you get when you look at stellar mass black hole through photons, right? Because you're probing different places with a messenger that encodes different information. Gravitational waves encode space-time, so you get information about distance and mass really accurately. Photons encode information like temperature, density, pressure, chemical composition. And so marrying these two messengers is going to be the most awesome thing ever. So you guys are at a really great time to live if you love black holes. All right, so now for the stellar mass black hole universe, we have some cool information. We have some demographics. We certainly can't measure all 10 to the 8 of these stellar mass black holes, but we have some information, and already some cool things are emerging. The ones that we have measured by EM photons So let me just map. This is nothing. This axis is nothing, and this axis is the mass of the black hole in solar masses. Okay, and the purple ones are the black holes that have been discovered, like Cygnus X1, because they shine really well. So the tracer is photons, and these are the black holes that have been measured via gravitational waves. And already you see a trend, which is the ones that have been discovered by gravitational waves are systematically higher mass than the ones that have been discovered by photons. So already we're seeing some surprises that we astronomers have to grapple with about how you create these black holes. And I'm not a member of LIGO, but I can tell you that right now, that LIGO's still observing, and they're getting big surprises. And so please stay tuned, because this picture may well be completely, it'll completely blow your mind, I would hope. Okay, so we know there's stellar mass black holes. We also know for sure that there are supermassive black holes lurking at the centers of basically every galaxy. And so I am not obsessed with Cygnus, but this, right, Cygnus X1 for the stellar mass black hole, Cygnus now for the supermassive black hole, they're two totally, they just happen to both be in the same region of the sky. This little picture here, there's a whole galaxy here, and what we're seeing is an X-ray image of that shiny accretion disk slash hot region around the supermassive black hole. You're seeing long jets, and then these lobes where the gas that is being ejected from the supermassive black hole finally hits the edge of the galaxy and can expand. So this black hole, if we talk about scales now, this black hole is, I'm going to say 10 to the 8. 10 to the 8 solar masses. Anybody want to correct me? You're welcome to. Is it 10 to the 9 or 10 to the 8? Yeah.
Well, I'm not going to figure out mass, but I'm going to say that's a radio image, not an X-ray image.
Oh, yeah, you're right. Sorry, I screwed up. Thank you. Yeah, and you can totally tell, right? Because the resolution's way better, right? No, X-rays are great, but just resolution is better for you. Thank you. Okay, so this is a gorgeous X-ray image of a galaxy. Let's say it's 10 to the 8 solar mass black hole, and the galaxy itself is this big 100,000 light years-ish, and these jets are outside the optical extent of the galaxy. Amazing power inside the centers of galaxies. And right now we're wondering, so one big mystery, I was asked to talk about mysteries. One basic mystery is, are there other types of black holes? Primordial black holes formed from inflationary epoch that may be teeny tiny, or astronomers are really big into now this middleweight black hole called intermediate mass black holes, because we're not super creative. But here's an example of a good candidate for an intermediate mass black hole. This little shiny thing here is, we think, a good candidate for an intermediate mass black hole that's about 500 or more solar masses. It has its own little clump of stars around it, and it's setting sort of on the outskirts of galaxies. So that jives perfectly well with a lot of theories of supermassive black hole assembly, but the hard part is that we actually have to measure the mass of the black hole quite accurately with some sort of kinematic tracer, and that's tough to do. So there's no great kinematic smoking gun yet for an intermediate mass black hole, but stay tuned, because things like gravitational waves are excellent at measuring masses, and so if there are intermediate mass black holes, we may expect future gravitational wave missions to give us some idea about that, if black holes in the intermediate mass black hole range merge. Okie dokie, so for a typical astronomer, when you find something like supermassive black holes at the center of galaxies, and you want to understand something about the underlying physics, we are a science that is just, we can't do direct experiments, so we wait for the data to come in, and typically what we do is plot every variable related against every other possible variable, and the thing that has the tightest correlation is supposed to tell you something about the underlying physics. What it tells you, not sure, but at least it starts to give us a hint. Okay? So here is the best and tightest correlation between black hole mass and something about the something related to the galaxy that it lives in. And so here's black hole mass, and for those of you who can't see everything here, this is about 1 million times the mass of the sun, and this is 10 to the 10. What correlates best is something called the velocity dispersion at the effective radius of the bulge of the host galaxy. So think of velocity dispersion in this case as kind of like a mass proxy, just for our purposes. It's not perfect, but whatever. The biggest deal, though, is that this mass, essentially, this velocity dispersion, is measured at the effective radius of the galaxy. Now, for our purposes, again, let's just think of that as the edge of the galaxy's bulge, the spherical part. And I'll go over size scales in just a second, but this, for an astronomer, is an amazingly tight correlation. It is as tight as you can get it, taking into account the observational uncertainties. So let's walk through this because it's so nice. These little ellipses mark the 1 sigma error bars in the measurement. So when I show this to my physicist friends, they will stop me here and they will say, Kelly, you have, order of magnitude error bars here in the black hole masses. And yes, that is true. We need to measure tracers as close as possible, kinematic tracers as close as possible to the black hole in order to guess a good mass or to measure a good mass, and that is very difficult, as maybe we'll hear later in the introduction. But nonetheless, sometimes we have order of magnitude error bars. Same thing with error bars in the velocity dispersion. Note there are places where it's especially difficult to measure the velocity dispersion, one of which is our own Milky Way. We know the black hole mass very well, as you'll hear in the next talk, but measuring our own velocity dispersion is kind of tough because we're in it. The different colors correspond to the different type of galaxy host, whether it's a spiral or elliptical, and there's little symbols here about the actual kind of tracer you use, like do you use gas near the black hole or do you use stars near the black hole, blah, blah, blah. So anyway, this is the tightest correlation. Now let me tell you how remarkable this is, because remember, sort of for a 10 to the 6th solar mass black hole, the place where a physicist would consider it to be a black hole is on the order of, size of the solar system-ish. The place where the black hole starts to dominate the gravitational potential is roughly a parsec. So a parsec is about 3 light years, and in terms of the size of the solar system, it's 1,000,000 times larger than that. Okay. The place where you're measuring the velocity dispersion here is the edge of the galaxy, which is a kiloparsec. In other words, it is roughly 10 to the 9, 1 billion times larger in physical scale than the place where the black hole exists. So the huge mystery that we have right now is that we do know that the black hole mass and the host galaxy co-evolve or are related, but it doesn't make sense why that would be, because those physical scales are decoupled and the mass scales are decoupled. So that is one mystery. There are certainly a lot of ideas, and let me really quick talk about one prevailing idea. And it goes like this. For supermassive black holes, they tend to grow through galaxy mergers. Galaxies grow through galaxy mergers. Here's an example of a simulation of 2 galaxies merging together, and the initial conditions of this merger were supposed to match a galaxy that we know called the antenna galaxy. I can show you a picture of that a little bit later if you want to see it. But what you see, I'll play this again here, are older stars and gas are sort of here. Sort of typical age stars are here. You'll see younger stars, forming in yellow. And so what you'll notice are 2 equal mass galaxies smashing together. You'll see that it looks a bit like a train wreck for some time. You'll get to see some star formation and gas inflowing. What you may be hard to see are some red bits here. That is energy feedback, is what it's called, from the black hole accretion, from gas falling into the black hole. So what is happening here is, under this prevailing theory, 2 galaxies merge together, gas flows towards the galactic center, the gas fuels the black hole, the black hole doesn't convert all of that into mass, but converts some of that into energy, and that energy feeds back into the surrounding medium, can push gas away, can heat gas up, and can regulate star formation in that way on scales that are much, much bigger than the actual galaxy. So that is one idea about how black holes and their galaxies co-evolve. But the jury is still out. There's still a lot of work to do about this. And one of those is that, well, one of those is an observational issue. Well, okay, fine. If galaxies merge together and there's a black hole in each galaxy, then we should be able to find black holes that are binaries, supermassive black hole binaries in galaxies. And right now, I think this is an observational issue. We're pressing the limits of our observational technique. I don't think we've hit a logical conundrum yet. But let me just tell you, while we certainly find two AGN, aka two black holes in one galaxy, good evidence that maybe there has been a galaxy merger. Like you can see, these guy seems to be in the throes of a galaxy merger. These seems more settled, et cetera. So you see two accreting black holes in galaxies. There are very few, maybe none, depending upon who you talk to, actual supermassive black holes bound together in a binary. Here's one great candidate that is, this is a radio picture. I'm always going to look at you when I see radio now. All right, this is a radio picture, a gorgeous picture of two cores that may well be two supermassive black holes that are separated by less than 10 parsecs away from one another. That's a great candidate. Oh yeah, you want to go ahead.
I mean, there's actually a lot more candidates than that nowadays.
Yes, I'm going to talk about that. Thank you. Promise. All right, so this is one great candidate. There are other candidates, but none that are shown to be bound together as a supermassive black hole binary yet. And part of the reason why is because the orbit is, tens to 100 years long, and we need to get a consistent, for example, radial velocity or spectroscopic confirmation. Here's another example. In the future, we're going to get a lot of great information about this. Here's another example of periodicity that may be caused by two black holes orbiting one another. Again, it hasn't been confirmed yet because one problem is that supermassive black holes flicker a lot. And so one has to convince everyone that the flicker is caused by variations in the orbit caused by two supermassive black holes, or is it just natural variation of one single AGN? And we need follow-up. So this is an area where we will have advances in the very near future. And there are other ways to look. If you're interested, please let me know. What I want to continue with are some observational fronts that are pretty interesting in my mind. And this goes back to that massive black hole velocity dispersion relation, which sometimes folks call the M-sigma relation, sigma meaning velocity dispersion. This is that. And so the cool thing recently, I think, is that we're finding deviations from this relation. And I think there's interesting physics in those deviations. Here's one example of an ordinary looking galaxy near the center of the Perseus cluster. And it, well, at least they started to say it had a 17 billion solar mass black hole, which was 60% of the total mass of the galaxy. And that would place that black hole here way off the correlation. Now, when folks followed up with different estimates of the mass, they brought the mass down, and I think there's still a little argument about the exact mass, but nonetheless, it's off the charts with respect to the M-sigma relation. And we're finding black holes in unexpected places as well. This is on the frontispiece of the talk. This is a tiny little galaxy called Henneis 210, and there are a bunch of little galaxies like that that are irregular galaxies, dwarf galaxies even, and they have million solar mass black holes at the center, which is synonymous with the mass of the black hole at the center of our own galaxy. So these are very small galaxies that have large black holes in them, and they themselves are a mystery to explain. You find black holes in low surface brightness galaxies. This is a beautiful low surface brightness galaxy called Malin 1, and it's got a supermassive black hole in it that it sort of defies expectations. And here are some other black holes that are roughly million solar masses in things that have very small bulges, and even some that have no bulges at all. So how would you put that on a relation that on the x-axis cares a lot about the spherical part of the galaxy if there's not much of a spherical part? So I would say one big upcoming job for those of us who love supermassive black holes is to complete the demographics of what do we have in our galaxy in terms of the mass of a black hole compared to its underlying galaxy and binary black holes. Okay. Let me turn to maybe some theoretical mysteries. So here are, black holes that we're finding at relatively close by. So that M sigma relation that I showed you all had black hole masses for galaxies that were at our present epoch, essentially. You can look for quasars and AGN, active galactic nuclei, very, very early in the universe. In fact, here is an example of a gorgeous black hole that we know is at redshift 7.5. Okay? And its black hole, which we can talk about the way in which folks measure black hole masses nonetheless, it is, rivaling 1 trillion solar masses. And that black hole, is in place less than 1 billion years after the Big Bang. So a huge question, a major question for those of us who love supermassive black holes are, how did the black holes get in place at large masses so early in the life of a galaxy? So in other words, how are supermassive black holes born? For those of you who are interested in how you detect supermassive black holes, I can talk to you about this later. Okay. Or lots of other people can in the audience. Okay, so that's me saying that same thing that I just said. So there's a bunch of ways to talk about sowing black hole seeds in the galaxies. I'm just going to go over 2 main contenders, neither of which work perfectly. So look, if you're a theorist who loves supermassive black holes, this could be a great place for you to work. One of them is called a lighter seed channel, and these black holes were formed from the birth of the first generation of stars called population 3 stars. So you form gas inside of a dark matter halo early on in the universe that's going to become a galaxy. The gas cools and forms maybe the first generation of stars. That star lives a very short time and then makes a first seed black hole. And those black holes are, folks debate about it, but it could be anywhere between 10 solar masses to a couple hundred solar masses, depending upon who you speak to. But those black holes were born at redshift 20, a couple 100,000 years-ish after the Big Bang, and so we only have a little bit of time to grow up to 1 billion solar masses from these black hole seeds by redshift 7, or 1 billion years. But nonetheless, these things may happen. We do know that these first stars shine, and they may help reionize the universe. So this is sort of a simulation of how the universe becomes less opaque, and you get to sort of make a Swiss cheese model of the universe. Many of the large black holes that we're seeing right now are in unusual spots of the universe where light can penetrate and reach us. So, so we're seeing kind of in the epoch of reionization right now. The remnants of those first stars, again, are going to be light seeds. But in order to make a 1 billion solar mass black hole, you might have to start off with a heavier seed, and so there's a sort of another channel for forming black holes, and that is called a direct collapse model. So basically, the gas inside of a dark matter halo cools, but it cools in a very particular way so that the gas doesn't fragment and make stars. So I can talk a lot about that in a little bit, but I have 3 minutes left, so I won't. But if you have questions, please let me know. So anyway, the gas collapses directly into a black hole, and that black hole could be about 1 million solar masses. So that is a great way to jumpstart the black hole seed mass. Just to let you know, I actually do research. Here's some research that we did that shows you this process in a simulation, so I can talk to you about that. And we found a surprise in that you can form many direct collapsed black holes in a single protogalaxy. So if you're interested in that, come visit. The beautiful thing about many of these questions, like how black holes are born, how long does it take the black holes to sink to the center to become a binary, to match our observations of binaries, which we still haven't made, our demographics, et cetera. Lots of these questions are just on the precipice of being able to be answered with future data. Okay? So happily, we have a whole new channel of being able to detect black holes, and very soon there will be a space-based instrument called LISA, which will launch in about 2034. I'm part of that, and I love it so much because it is designed to detect mergers of supermassive black holes. So remember, ground-based gravitational wave detectors detect stellar mass black holes merging. LISA is a space-based instrument with arms that are basically 5 million kilometers-ish separated. And those long arms mean you detect long wavelength gravitational waves or large black holes smashing together. And the great thing about this is that we now have a new set of parameter space that are exactly tuned to supermassive black holes like the ones we have just talked about. Here's a little plot that talks about the ability of LISA. The real logo doesn't have a heart around it, I love it. And so this is redshift. This little mark here is that place where the universe is opaque, so ish. And here is the total mass of the two black holes smashing together. Okay. These little things mark current LIGO. So current LIGO can detect these kind of mass black holes in the local-ish universe. There are future surveys that will be able to detect very massive black holes, and I haven't had a chance to talk about them, but they're also incredibly awesome. These little contours are contours of signal-to-noise ratio for the types of black holes and distance that we're talking about. Okay? So here's what I want you to take away from this. The types of black holes that sit in galaxies like our own, these 10 to the 6 solar mass black holes, when they merge together, they'll be able to be seen with with signal-to-noise 2000 out to redshift 6, which is amazing. So we'll be able to get the demography of merging black holes out to incredibly large distances. And the thing that always makes me want to drop the mic here is that you can get signal-to-noise 500 of two 10 to the 6 solar mass black holes merging together out at redshift 20. Okay, so back into the region where electromagnetic radiation cannot probe, you get this whole new channel of data that will be able to tell us precisely about how black holes are born. So if we have large seeds, and they merge together, we would be able to detect them really, really loudly. And there are future telescopes that will also, ground-based telescopes, that will be able to detect this light solar mass seed channel called the third generation of detectors. So we have a way very soon to be able to answer the question about how supermassive black holes are born. Okay, so I'm going to end with, wow, it's great to be us. We have a lot of work to do, and it's not inconceivable that we will be able to do it because we have data, we have simulations, we have theory that are all coming together right about now for us to be able to attack these great questions. So we need to get robust supermassive black hole masses. We need to understand supermassive black hole binaries and get a good sample of them that are, rock solid. We need to understand this supermassive black hole galaxy correlation. Remember I said we found a bunch of outliers, and those outliers may tell us something. We don't know how black holes are born. We also don't know how they grow. We will hear a little bit about accretion and feedback, but I would say that's an unsolved question as well. We don't understand how black holes merge together, and that's something I didn't talk about, but I'm happy to. And astronomers don't often think about spin, which encodes a bunch of incredibly amazing information about the dynamics of the process, but we are just on the precipice of being able to detect spin, so we don't talk about it as much. And that needs to be incorporated into our physical models. Okay, so thank you very much. If you have questions, holler.